Thank you for joining the Resilient Cyber Show. My name is Chris Hughes. Today I'm joined by Christoph Kern. Christoph, thanks for being here.
Thank you, Chris, for having me. I'm excited and looking forward to the conversation here. It should be an interesting discussion.
Yeah, likewise. The topic of security by design has been a hot topic in the industry, from CISA to security leaders like your organization there. So I'm curious, for folks that don't know, you haven't come across some of your publications like I have already. Tell us a bit about your background, what role you're in now, and kind of how you got to that.
Yeah, so I've been a security engineer at Google for really quite a long time. I've been there about 20 years or 20 years and a bit. I sort of, I guess ended up working primarily on secure design, just based on sort of a history of, in the beginning, doing what you kind of do in application security, which is to do code reviews, pen testing, and basically looking at the security posture based on finding defects, right, and then trying to fix them. And at some point, I was sort of getting tired of looking for the same type of vulnerability over and over again, like cross-site scripting and cross-site request forgery in web applications, and other common classes of vulnerabilities. And so it sort of started bugging me, basically, that we're sort of never getting ahead of the problem. And I started thinking about whether or not there's ways to treat these in a bit more proactive manner, in a bit more principled manner, and try to actually address them as a class and try to find a way to architect software, to build software in a way that avoids introducing these defects in the first place, right? And it took quite a long while to figure out how to actually do this in practice, right? I mean, there's lots of academic work that talks about these kinds of things, but turning this into practice in a real software development environment, especially at the large scale of Google with tens of thousands of developers, is a different story. And so there's a lot of sort of nuance on how to actually make this work in the real world at acceptable cost as well. And so it took quite a while to figure this out. But I think over the last decade or so, I feel like we've sort of hit on some practical design patterns that really seem to work very well and are also practical and cost effective at scale.
Yeah, I mean, I would say, and I'm sure many other practitioners like myself would argue, your organization has a pretty good reputation compared to some industry peers of similar size, in terms of security track record and capabilities and so on. You recently published a paper called Secure by Design at Google, which got some great attention from organizations like the Atlantic Council and others. I'm curious, how did the paper come about, and what were some of the kind of key themes that you were emphasizing in the paper there?
Yeah, so I think the reason we wrote this is that, we've been basically working on these things for, well over a decade. And we've, published some more academic papers or articles in sort of more technically focused publications of how we went about this. But I, with the sort of the topic being more a topic of discussion in the industry, as well as government entities like CISA, we just thought it'd be a good time to be part of that conversation and basically wrap up in like a sort of like a self-contained publication how we think about this problem at a high level, and how that maybe differs from some of the approaches that traditionally have been taken. And so, if I sort of were to just sort of summarize, I think perhaps one of the sort of key things in there is to really look at the problem holistically and not look at it just as a technical problem, right? And look at it as sort of the combination of a technical problem and a really people problem, like a human problem, right? And I think a lot of issues continue to arise because there is a lack of recognition that we're basically designing products as well as development processes in ways that put an unreasonable burden on humans to not make mistakes. And that just doesn't seem to work, right? I mean, humans are humans. They will sometimes forget things. They will sometimes make a mistake. They will sometimes not have read the guidance because they didn't have time for it. And in some cases, the sort of reasoning you're required to do to avoid a mistake is just really, really complicated. And it's just sort of an impossible task for people, right? And I think we basically have to sort of step back and just take that into account first and foremost, and try to work around that. And I think there is sort of a maybe some sort of lessons to be learned from safety engineering, right? When we're looking at the safety of products, where if somebody makes a mistake using it, they actually get hurt. There's a lot of practice in thinking about how to design products so that they don't expose users to their hazards. And so we've been kind of trying to think about this in a similar vein, except, usually people don't get actually hurt. And if a developer makes a mistake, they don't get hurt, but they might introduce a defect into a product that then causes a security risk later on, right? So the hazard is different, but it's still the thinking is basically that a design of a product or a developer tool exposes you to the potential for something going wrong, and we need to think about ways of changing design so that this likelihood is reduced, or ideally as much as possible eliminated.
Yeah, and I think that the theme you're getting at there of comparing it to some other environments and other domains, like the resilience-based thinking, is something I've seen quite a bit from one of your peers, Phil Venables, for example, is often advocating these kind of ideologies. In the paper, you also discuss some unique aspects of software, how it's different from mass-produced physical systems. For example, you talk about the dynamic and iterative nature of software. Now, on one hand, you mentioned how the risk of introducing a new defect over time for a physical system after you manufacture it and kind of distribute it is likely on low, unlike software where it's more iterative, it's more dynamic, it's more ephemeral, for example. And I know Google is big proponents of, say for example, Adora metrics. And some of those papers have shown that organizations that are, more capable of routinely delivering software to production at scale actually have more resilient systems. So I'm curious, your take on, it seems like there's a double-edged sword. On one hand, you can't introduce a defect of a physical product after you manufacture it, but also it's a lot harder to kind of recall, iterate, make improvements, after something's kind of been distributed. Where software, we have that luxury, right? For example. So I'm curious on that double-edged sword. I'm curious your thoughts on that.
Yeah, that's a really good question, and it's an interesting sort of way of looking at the problem, right? I think in some ways, software really is very different from the manufacturing of physical products. And in particular, I think people often tend to think of coding, of implementing software as sort of more a manufacturing process. But I think it is actually sort of, in some ways more of a design activity, right? So if let's say you have a CAD file of some, artifact and you send it to the metal shop to make it, that is a very precise specification of what you want, right? And if you send the same file to two different shops, you probably will get back something that is very, very similar. I mean, it should be basically almost indistinguishable, right? If your specification of what material to use and so on is fairly complete, right? Versus software specifications are much, much more ambiguous, and the process of implementing really is a lot of like design refinement and still design work, right? And so there's a much less prescribed outcome. And so probably if you give the same sort of typical industry software spec that's pretty loose in textual description of what you want to do different developers, you'll probably get two very different programs, right? And so then if you couple that observation with the fact that as you're implementing software, you're in a typical software development environment exposed to a lot of opportunities to make choices or mistakes that result in potential defects, security defects, as well as reliability and correctness defects. You basically have this sort of creative process, this design process that is just exposed to a lot of hazards, if you will, right? And so then if you look at it from this perspective, it's just basically unavoidable that these defects will appear in the end product, right? The actual sort of really true manufacturing aspect of software, which is basically running the compiler on your source code and then shipping the product, really is not that prone to introducing defects, right? I mean, I really have a hard time thinking of a case where, let's say, a compiler bug resulted in an exploitable vulnerability in a binary, right? I mean, that it happens, but it's extremely rare compared to the prevalence of defects that really arise from sort of an inappropriate choice in that design refinement process that is coding, right? And so I think if we now look at it from the sort of resilience perspective, and as you mentioned, the other thing that happens then is that you don't just do this once and then ship it in typical industry software, right? In sort of in software in the industry that I'm in, it's very common to continuously improve software and basically have like weekly releases, and so you have this sort of ongoing change that a priori always comes with a risk of introducing defects. And so I think basically in that light, we have to start sort of looking at the maturity of the processes that we wrap around this development to really reduce the risk of accidental introduction of these defects. And so since you sort of mentioned the sort of maturity models for the developer process, those are really then the levers we can use, and we can maybe dig into that a little bit more in detail, right? If we're delivering software on a very regular cadence, that really forces us to have a lot of automation around aspects of that work that commonly result in problems. And if we're sort of taking that view and pushing that sort of further left, we can look at classes of problems as they arise in this whole process and try to find ways of automatically preventing changes that introduce defects.
Yeah, and you talked about, it kind of emphasizes the need for secure by design, because as you point out, it's more of a creative, design-oriented endeavor than it is kind of the rigid manufacturing scenario where it's like, it's very repeatable, it's very standardized. Software is much more creative and design-oriented, as you said. You talked about some of the, frameworks, for example. I'll just pull a thread on that. We've seen a big push in the industry, for example, especially in the public sector where I spend a lot of time. Or rallying around things like NIST Secure Software Development Framework, which pulls from things like BSIM and OWASP SAM, but each of those are different too. You have some that are prescriptive or descriptive, or some that are very, rigid. So I'm curious, like, how valuable or useful do you think those are? And then also, how do we kind of approach that as an industry? Because every organization has unique capabilities and resources, and maybe using different frameworks, so it can get very complicated too at scale.
Yeah, I think these frameworks are helpful in that they put sort of a scaffolding around how you look at the end-to-end problem, but at the same time, I think they still do have gaps or areas that they don't fully address in a way that seems to work, right? So in particular, if you look at the SCF, there's a lot of focus on processes, and those are helpful, but they still inherently put the onus on people to always follow the process and never make a mistake, right? And that works well if the opportunities for mistakes are rare, and it's a part of the process that really doesn't happen very often, doesn't happen every week, and it's something there where you can really get some people who are experts to spend time to focus and really dig into the problem. Then you'll get good outcomes, right? So if you're, for instance, talking about high-level architecture, or how we are like designing, authentication or authorization for a new system or whatever, right? Like that's something you will do once for that system in the beginning, and if you get experts involved at that point and really do a thorough exploration of the problem space and really digging into the topic, you'll get good outcomes, right? But on the other hand, if you're looking at defects that arise from opportunities to make mistakes that appear very regularly in the activity. So for instance, if we're looking at common implementation bugs like memory safety bugs or cross-site scripting in web applications and so on, those ones tend to not be very amenable to processes, right? Because they're the opportunity to make a design choice or a coding choice that results in a defect presents itself very, very frequently throughout the workday of a developer, and just assuming that they will never make a mistake or never miss anything is simply unreasonable, right? And so this is sort of an area where just a layering process and documentation and developer education doesn't really seem to work all that well in addressing that risk. And so that's an area where we have to then layer more technical mechanisms on top of the process to really reduce the risk of these sort of types of defects, right? And so this is sort of where the discussion of developer ecosystems and designing those comes into play, right?
Yeah, and I'm going to get to that paper in a moment, the second paper that you recently published. But in the initial Secure by Design at Google paper, you also talk about the need for secure default configurations, which is something you kind of touched on there. It feels like the mantra you likely have heard, guardrails over gates, right? We hear that kind of used in security lately. But historically, it feels like producers of software have kind of erred on the side of functionality and usability over perhaps secure default configurations. And we've even heard CISA start to advocate for terms like loosening guides rather than hardening guides. But that could be problematic if you're trying to, think about the customer experience or the developer experience in some cases. Do you feel that the two concepts of security and usability are inherently at odds, or do they need to be per se?
I mean, to some extent, you could sort of take the point of view that a product that is not easily usable in a secure fashion is not very usable, right? Like, so if you're, I think in a lot of cases, these sort of secure design choices and what defaults of security settings are in some ways punting difficult decisions onto the user, and that's actually not very user friendly, right? And this applies both to sort of enterprise facing products as well as end user facing products. And so I think this comes back to sort of what we talked about in the beginning, the user centric view, right? You really have to, in the design of the product, think about what is a reasonable expectation for your typical user to navigate that particular problem, right? So if you're looking at products that are delivered to the general public, you really just should not assume any kind of technical background or security knowledge, right? And it's really then up to the designer of the product and the vendor to try and figure out ways to make the product usable in a reasonably safe fashion, even if the user doesn't know anything about security, right? And so, for instance, like we see these guidance, well, be very careful which link you click on, only click on safe links. That's kind of a really unreasonable thing to say, because like, how would a member of the general public be able to actually assess whether or not a given link is safe, right? You just can't do that, right? It's so it's such an unreasonable thing to expect for people to be able to do. Even technical people might have trouble with this. You kind of have to be a software engineer to really think about what happens when you click on a link and what happens in a network level. Does the link text even correlate with where the link goes? And does the URL actually tell you anything about whether or not it's safe to click on? It usually doesn't, right? And so I think from that perspective, it really is actually part of building a usable product, is to design it so that basically users can click on any link and nothing terribly bad should happen to them ever, right? And then that sort of informs how you actually design that software and how you make it resilient to malicious servers, and how you make it resilient to network level attackers, and how you make it resilient to malicious websites and spam and all kinds of abuse, right? And so it sort of informs the entire shape of the product, basically, if you take that perspective, right? Versus just throwing up a warning to them and then sort of assuming it's out of your hands, and if they click it away, it's their fault, right? It's not their fault. They weren't really equipped to make any meaningfully informed choice.
Yeah, you're kind of getting at themes that I hear from the CISA, guidance and publication around secure by design, which is, kind of taking more onus or accountability for the security outcomes of customers. If you look at other products like, automobiles, for example, imagine if like everyone had to be an automobile expert to safely utilize an automobile, for example. It's like, but when we look at software, as you point out, we kind of just put the onus exactly on the customer. It's like, hey, you got to do all these things to be safe, but you can go ahead and use this. It's not really a forethought. And in the paper, you also talk about something that jumped out to me is you talk about developers or users too, and I feel like this is even more pertinent when we see the rise of software supply chain attacks and the realization that most defects are introduced by developers, and they're also in the best position to actually kind of address flaws and vulnerabilities. How critical do you think it is? And you've talked about this a little bit already. But how critical do you think it is to design systems, with that developer experience in mind?
Yeah. I mean, to me, that is really, and it comes back to what we talked about before, right? I think in this case, if you're looking at the, I thank you, Bob. I will. I think if you look at a developer's sort of daily work, they're interacting with a bunch of tools and systems, and also the foundational libraries and frameworks that they're building software on top of, right? And historically, this environment in which they're developing has been set up in a way that turns out to basically, again, put the responsibility for writing code in a way that is not vulnerable on the developer, in a way that is really not just realistically achievable for any human, right? And so if we step back from that, we kind of basically can take the view, and this is what Bob points to here, is that the design of the end-to-end developer ecosystem really very strongly informs the outcome. And how much we train developers doesn't actually seem to change this very much, right? So if your developer is working in an environment that is prone to the accidental introduction of vulnerabilities, you will have vulnerabilities in your shipped product. And if you can change the design of that developer ecosystem so that it is much less prone to the accidental introduction of defects, you will have fewer defects. And in our experience, that is really like the only thing that really dramatically changes your residual defect rate in the end product, right? And so, I mean, if we have time, we can maybe sort of dig into a little bit what this actually looks like for a specific class of vulnerabilities. I mean, my memory safety is probably an interesting one, as well as maybe SQL injection is an easy one that we can talk about that hasn't been talked about externally as much, but where in the end, a relatively simple change in the APIs and the sort of relevant parts of the developer ecosystem really resulted in a very drastic decrease in the residual defect rate, right? So
please do take a moment to talk about these common weaknesses and enumerations. Just picking one, like SQL injection or
so let's start with that one, right? So SQL injection basically arises from the shape in a way of query APIs that developers interact with or use when they write code that queries databases, right? And essentially the design of that API is that you give it a string that is then interpreted as a query in the SQL language and parsed and evaluated. And this API comes with the sort of implicit I guess, burden on the developer to write the code that constructs the queries so that no untrustworthy external inputs, no potentially malicious inputs are concatenated into the query. And if you do that, then you usually have a SQL injection where this untrusted input can change the meaning of the query. It can add additional clauses, or it can modify the, for instance, where clause, and then select more items than where intended, right? And so and so this sort of coding pattern of constructing queries from snippets, from like little pieces of query syntax is very common, right? Like it's very common to have a product that exposes something that has sort of a filter for, let's say, orders or catalog items. And depending on which filter setting the user chose, you end up with corresponding parts of the query that are being interpolated in that. And then it's very, very easy to accidentally make a mistake where you incorporate the externally arriving parameter just as a plain string, and then if that string is instead of just a number, for instance, is actual SQL syntax, an attacker can often exploit that to make the query do something that was not intended by the programmer. And for instance, select rows that actually belong, like rows of an orders table that belong to a different user, for instance, things like that, right? And so so essentially the risk of accidental introduction of this type of defect arises from the shape of the API. And so we basically sort of thought about, like, can we change the shape of the API so that this risk goes away? And what we actually came up with after a while of thinking about this turned out to be extremely simple to implement. We basically, we sort of wrap this API in one that is exposed to our developer population, where the API no longer accepts a plain string, but rather accepts a custom vocabulary type that represents a query that is safe to use. It represents a string that is safe to use as a query. And then we provide builders for this type for queries that are constrained so that you can't append an untrusted arbitrary value. You can only append, for instance, trusted parts of the program, basically string literals, right? The interesting thing is that the developer experience doesn't actually change very much, right? You're still basically appending strings into a query. The only thing you're not allowed to do anymore is to append a string that comes from an external parameter or some other unknown origin, right? So in terms of developer ergonomics, it actually works really well because your general coding patterns on how to interact with the database really don't have to change very much. You just have to use the trusted SQL string builder instead of a plain string builder. But overall, your code structure won't change very much. But with that change, we now get very high assurance that code that does not follow these sort of safe patterns of only incorporating trustworthy strings into the query basically won't compile anymore, right? So if you deviate from the safe pattern, you get a compiler error and you just fix it and you're on your way. And so with this change to the shape of the API, we got to the point where basically, I mean, we introduced this probably like 12 years ago or something. And to the best of our knowledge, and we made this sort of, we just made this the API for anybody in the Google internal developer population who interacts, for instance, with our large scale spanner database. That's the API you get to use. There is no other one. And to the best of our knowledge, we've never had a reported SQL injection vulnerability in that code base anywhere, right? With thousands and thousands of developers. And conversely, if you look at the CW stubborn vulnerabilities, I think SQL injection is number 3 on their list, right? So it is definitely a significant problem. It doesn't happen very often, but if it happens, it's often a pretty high impact catastrophic vulnerability that might allow an attacker to sort of suck down your entire database, right? So this is an example where really in hindsight, once you figure out the pattern, in hindsight, a relatively straightforward and simple change to an API drastically reduced the risk of accidental introduction of that vulnerability. And it turned out to be actually, in this case, really quite cheap, especially at the scale of Google, right?
So yeah, I mean, you're using it. You gave a really explicit example of how you fix a widely systemic and pervasive, common class of vulnerability at a scale that most organizations simply aren't even having to, wrestle with. I wanted to ask you about the scale. Some may push back and say it's easy for Google to say this. They have the incredible expertise and wealth of resources to go and address these kind of things. But conversely, Google also has a scale in terms of challenges that most organizations simply aren't dealing with either. Now, how do you kind of balance the two between that? Obviously you have the amazing resources and expertise, but you also are dealing with things at a scale that most organizations simply aren't either.
Yeah, that's an interesting question. I mean, I sort of get the sense, I don't have any real statistics to back that up, but just sort of informally, I sort of get the sense that the ratio of security engineers to developers is actually pretty similar in organizations that are large and small, right? You're basically, as a security engineer, you're always outnumbered by developers by a factor of, probably tens, hundreds, depending on what that is, maybe like several hundreds. It sort of depends on exactly how you count, right? And so, while Google is a lot bigger, in some ways, the problem is just sort of scaled up, but not fundamentally harder or easier, right? One sort of big lever and advantage that we get is from that scale is that the scale really forces you to be much more principled about your developer workflows and sort of have like some of these DORA capabilities, like working from a central repository and having regular cadence of releases and having centrally maintained tool chains and so on. And those are actually the capabilities that you can then layer on what I just talked about, for instance, with this sort of type-based approach for preventing injection vulnerabilities. This really only works because we have a monorepo where there's one copy of the API and we change it. Everybody else all the developers have to use that, right? There is no way around that, essentially. And so just having that underlying capability in the overall developer ecosystem then makes it possible to layer on a mechanism that addresses a class of vulnerabilities with really relatively small incremental investment. And so I think if you're in an environment that is really very ad hoc and you you just pull components from all over the place from the internet, and you don't have a sort of reasonably well structured development and deploy and release flow. These things are difficult, but if you have it, then layering that on top is actually really very feasible and very very cost effective.
Yeah, can I ask you a question and deviate from the technical topic slightly? As we see this push for secure by design, obviously it's largely been kind of a voluntary effort, like the CISA Secure by Design pledge is a voluntary pledge. Many have, said it's great that we're going this direction, but organizations are all typically only going to do what they have to do or are required to do from an investment perspective. And you pointed out like a good example of, how you can efficiently fix a widely systemic class of vulnerabilities, but there are some cases where it takes significant investment, right? Of time, energy, resources, manpower, whatever the case is. How do you think that is or will play out if it stays a voluntary, rather than being compliance or regulatory driven kind of scenario?
Yeah, that's a good question. I'm not sure if I have a really thorough insight on that. I mean, I've been sort of, I guess, fortunate to work in an organization where this isn't really a question, right? Google is big enough, and it's just sort of obvious to everyone, leadership and engineers I work with, that that security is a high priority because we just have a clear responsibility to make that a priority and make the investments, make the long-term investments to live up to that responsibility. I think for small software shops, it's an interesting question, right? There's just so many demands on different, in terms of different priorities on these organizations, and security is just one of many, and it maybe is one that doesn't really rise to the top until you gain a certain exposure, right? Like if you're just basically starting out and you have very few users, the impact of a mistake is just inherently bounded in terms of the broader societal impact. And then as you grow, all of a sudden it becomes much more urgent because the scope of impact is increased, right? But then it might be too late because you've already made design choices that are difficult and very costly to undo. And so I think, I don't know how to really address this. I think over time, I think one observation perhaps is as we were rolling these approaches out in Google, in some cases, like in the SQL example, we were just able to basically talk to the team that owns that API and change it, convince them that that's the right thing to do, and we can do it in a way that doesn't impact their users negatively, their developer base. In other areas, for instance, web security, the work we needed to do really happens more at the web application framework level. And there used to be a fairly large number of frameworks in Google that have just arisen organically or derived from open source frameworks and so on. But then over time, it sort of turned out that this diversity of frameworks is just kind of really costly and actually not effective for developers. And really for primarily not security reasons, a convergence on a well-maintained and centrally supported framework started to happen. And then we were able to work with that framework and build all these kind of secure by design and secure by default structures into that. And developer teams kind of flock to that framework because it solves a whole lot of problems to them, one of which is security, but also it just does all the right things in terms of how you structure your cadence of test and staging and production environments. And it really addresses sort of a lot of the common problems that every development project needs to address, and it does it for you, right? And so I think maybe one avenue to kind of address this is to really focus on popular frameworks that developers gravitate to, and work on improving those and making them inherently more secure and less prone to the accidental introduction of vulnerabilities. And then we might actually get somewhere at scale, right? And I think we've started seeing this happen, right? Like, so some of the work we did in web security, for instance, we actually turned into a browser feature called Trusted Types, which is sort of a similar approach for web-based injection vulnerabilities like XSS, that's very analogous to what I just talked about for SQL injection. And this is now a web standard, and commonly used web frameworks like Angular and React have become interoperable with that or compatible with that. And so if you use those frameworks and you turn that on, you actually get a very high assurance that your application is resilient with respect to cross-site scripting vulnerabilities with very little incremental effort, right? So it sort of comes down to choosing a framework that has these things built in. And then from a security perspective, it's about finding the frameworks that people tend to gravitate to and trying to make them, improving them in that respect. And I think that's sort of where maybe some of the scalability comes from over time.
Yeah, I like your point a lot. In a very short way, it almost felt like you said, make the right thing to do, the easy thing to do, and also like focus on widely pervasive used components of our ecosystem when we think about software development, and prioritize improving those from a security perspective, and you can drive adoption, right? Because it again makes the right thing to do, the easy thing to do.
Exactly.
And I want to ask you, one question or one thing we've seen come up a lot in the secure by design discussion, the national cyber strategy, and other things from CISA and others is the role of the most widely pervasive, largest software suppliers. And I'm curious, what role do you think the organizations such as Google of the world and others have to play in this ecosystem, given that so many, just you talk about web frameworks, for example, so many people rely on things that you all produce or have an influence on, and it can drive a systemic impact across the whole ecosystem when we think about security. I'm curious how you feel about that.
Yeah, I mean, I think, large organizations like Google are basically big enough that we can afford to make long-term investments in these kinds of things, and basically like actually have a couple of people spend 10 years. That's very expensive, right? Like, I mean, like a few decades of software engineering years, that's a lot of money. But at our scale, we can actually afford to make that investment and really try to find better ways of building software in a much more secure fashion, and also focusing on addressing common types of problems and so on, right? So and then as we do that, what we learn then over time hopefully trickles out and becomes more generally useful. And in some cases we can open source the code, or we can do things like what I just mentioned, like improve platforms like a web platform itself. I think the other aspect is that large organizations are often key partners in ecosystems like the internet and the web, and actually have the ability to nudge and influence the design of these ecosystems towards better places, right? So for instance, I mean, one example is there used to be a lot of trouble with inappropriately issued certificates, right? And at some point, some people at Google basically invented certificate transparency to address that problem, and that's now part of the web ecosystem, and it's built into browsers, right? Or some of the web platform improvements that I just talked about. So there is I think an opportunity to do these kinds of things that would be very difficult for a smaller organization, just because they wouldn't have the reach and they wouldn't have the sort of like level of involvement in these ecosystems, right? So I think there is things that organizations the size of Google can do that maybe nobody else really can, and so I think we're kind of conscious of that, and we try to actually do that where it's possible and where it's reasonable.
Yeah, I think you gave pretty several specific examples, and for someone that's been involved in software and cyber for a couple decades, I think Google's a good steward and example of that. And one thing I think of right away is like the terminology around the cloud shared responsibility model. You guys start championing like a shared fate model, right? Well ahead of others, and well ahead of some of the widely pervasive impacts on other CSPs that we've now seen play out, for example, and the impacts on customers and society. So I'm definitely a big fan of what you all do there at Google. So I want to take us to our final question that I ask everyone is, what does the term cyber resiliency mean to you?
Sorry, say again, cyber
resiliency. What does that term mean to you?
Yeah, I think so that's a good question. I think I would let me think about that. I mean, I think cyber is sort of a broad topic, right? Interestingly, I just reread this book about the sandworm. I think it's called Sandworm, right? It came out like many years ago, but I just finally got around to reading it. I skimmed it before, and basically, the work we do as software engineering organizations really has a pretty pervasive relevance to society, right? I mean, we kind of tend to not, in my line of work at least, most of the work is not safety critical, in the sense that if something goes wrong, people immediately get hurt or are at risk of getting hurt. It's not like avionics software or whatever. But at the same time, still, if there are defects, they do have the potential to very broadly affect societies and individuals, and sometimes have a fairly large scope of impact, right? Like, I mean, if you look at some of these like broad attacks on energy systems and ransomware attacks that basically disable shipping companies at scale and so on, right? I mean, it's a really broad potential for impact, and so I think it's sometimes easy it's sometimes tempting as a software security engineer, just look fairly narrowly at your product or your the particular class of problems that you're currently dealing with. But I think it is important to step back and see sort of how does this fit in the big picture, and how do we think about the resilience of societal systems that rely on technology as a whole, right? And interestingly, I mean, there's some interesting sort of observations at the end of this book in terms of actually specifically designing technical systems and software systems so that we actually kind of assume that they will sometimes go wrong, and we design how they are embedded in a broader structure, in a way that broader structure is still resilient to failure, right? Like, because that's really what we care about. Like, we care about we don't care about a particular vulnerability being exploited. What we care about is what is the impact of that. Does this take out power distribution, or does it compromise a large number of users' private data and so on, right? And so I think it's kind of worthwhile to look at the sort of broader impact of a potential failure. Think about, like, can we actually design the overall structure so that the potential impact of failure is somewhat contained and minimized, right? Because we will never be perfect, right? I mean, there's always going to be something that we missed, or that even approaches that I talked about, might have gaps occasionally, right? We can reduce. We definitely now know that we can reduce the residual rate of defects very, very drastically to very, very near zero. But I don't think we can claim that we get it to 0, right? That's just extremely difficult.
Yeah, you well said. It's not going to be the elimination of risk. It's the kind of mitigation of risk to a level that we deem as acceptable, and then building resiliency and fault tolerance into our broader digital-driven society that we all now live in. And for folks that the book is called Sandworm: A New Era of Cyber War and the Hunt for the Kremlin's Most Dangerous Hackers. I think it's the book Christoph is talking about. It's a great read, a classic. So Christoph, thank you so much for joining us. We talked about everything from secure by design at Google, the role of outsized largest software suppliers in our society, developer ecosystems for software safety, specific classes of vulnerability and the ability to eliminate them. So thank you so much for tuning in, to everyone who joined us. Thank you, Christoph, for joining us today.
It was a pleasure. Thank you. Thank you for having me.